Hi everyone! In this video we're starting a new chapter on carboxylic acids and their derivatives. So carboxylic acids, remember, have a carbonyl group with an OH on one side. The other side could really be anything. And by derivatives we just mean something that is created from an original compound. So if you start with a carboxylic acid, what we're going to find in this chapter is you can create all sorts of derivatives or compounds that come from a carboxylic acid, or they're derived from that carboxylic acid. So here we have an acyl chloride, an anhydride, an ester, an amide, a nitrile. So there's all sorts of different groups or derivatives that we can make. Down below, we also have an alcohol. We can also then go on to make an aldehyde or an amine. So there's all sorts of different things we can do here. But first, I just want to review some aspects of carboxylic acids, so some reactions we've seen before, and then I also want to talk about nomenclature. So let's start with nomenclature. So this is pretty similar to what we've seen in the past. You try to find the longest carbon chain. Now, in this case, a carboxylic acid functional group will always be at the very end of the chain, similar to an aldehyde. And that's just because we always have to have that OH group on one side. So that's just naturally going to put it at the end of a chain. So we'll start by numbering at the carbonyl carbon and work our way over. All right, it looks like we have 6 carbons here. So the parent chain is called hexane. But because we have that carboxylic acid, we're going to drop the E and add oic acid to the end. So not too bad. Now, there are some compounds that have common names that are accepted by IUPAC, the committee that decides all these naming rules. So let's just write some of those down because you will see those more often than not. So let's start with formic acid. So you might remember from our aldehyde chapter, we talked about formaldehyde, which had 2 hydrogens on either side of that carbonyl group. Here we have formic acid, where we have a hydrogen on one side and an alcohol on the other. The next one has a methyl group on one side, and this is called acetic acid, which is in vinegar. And then let's just draw some more. This one with 3 carbons in its chain is called propanoic acid. And then we've got butyric acid, which has 4 carbons. And then finally, if you have a benzene ring attached to your carboxylic acid, that is called benzoic acid. So these are just good to know. You could make flashcards for these because you will see these quite often. Now, we can also have 2 carboxylic acids in a chain. And these also have some common names. So let's say you have a 2-carbon chain and 2 carboxylic acids. This is called oxalic acid. Then if we add another carbon, so now we have 3 carbons in our chain. This is called malonic acid. Let's add another carbon. This one is succinic acid. All right. Add one more carbon, and this becomes glutaric acid. So if you're taking a biochem class or you have taken biochemistry in the past, some of this might sound familiar. Some of these are present in things like the citric acid cycle and other biochemical reactions. All right, the next one we're going to draw, we actually synthesized in one of our labs, I believe last quarter. Time keeps slipping away from me, so I forget when we did things. Let's see, so this is adipic acid. And finally, our last one is polemic acid. Or, oh, oops, I spelled that wrong. Pimelic acid. So that should be Pilemic. Now, these are also good to know, so you could make flashcards for these. I'm not sure how to remember these that well, other than there is an acronym you could use, so OMSGAP, Ohms gap, and then you could just try to remember what each letter stands for. But otherwise, there's not really a great way to memorize these other than to make some flashcards. All right, let's look at or review information about the structure and properties of carboxylic acids. So let's just start by drawing a generic carboxylic acid. That R group could really be multiple things. Maybe you have an alkyl group attached, maybe you have a benzene ring with other functional groups attached. There's all sorts of possibilities there. Now, the pKa range for carboxylic acids is from 0 to 5. So remember, low pKa values means that something is very acidic. So carboxylic acids can be quite acidic. It sort of depends on what they're bonded to. So remember that when you remove that hydrogen from our carboxylic acid, you get the conjugate base. And that conjugate base is stabilized through resonance. So the more stable the conjugate base, the stronger your original acid. All right, now your textbook talks a little bit more about the acidity of carboxylic acids depending on what's bonded to it. So if you want to read through that, I highly recommend it. But we're going to kind of just move on. Let's see. So let's review how to prepare carboxylic acids. So this is information we've already learned. One way is to start with a primary alcohol, and then you can form a carboxylic acid. Another method involves toluene, or at least something with a benzylic carbon. So remember, a benzylic carbon is one carbon away from a benzene ring. And that can form a carboxylic acid. You could also start with an alkyne and form a carboxylic acid. Or you could also start with a cyanide group and turn that into a carboxylic acid. All right, so see if you can remember the reagents that you would use to perform each of these conversions. So you can pause the video, see if you remember these reagents. So what would go above and below the arrow? And when you unpause, we'll go over it together. All right, let's start with the first reaction. How would we turn a primary alcohol into a carboxylic acid? So it looks like we are adding an oxygen, so that means we're oxidizing our primary alcohol. What oxidizing agent could we use? Well, we want a strong oxidizer, right? A gentle oxidizer would stop at an aldehyde. So our strong oxidizing agent would be something like chromic acid. All right. Let's see our second reaction. We want to turn toluene into a carboxylic acid or benzoic acid. And again, it looks like we're oxidizing, so what reagents would we use here? So if we're trying to oxidize the benzylic position, we could use something like potassium permanganate, followed by sodium hydroxide and water as well as heat. Okay, what about our alkyne? How would we turn an alkyne into a carboxylic acid? Well, I'm noticing right off the bat that our product has less carbon atoms. So let's see, 1, 2, 3, 4 carbons are in our starting material. I mean, the R groups could contain more carbons, but we'll just say they just have one for the sake of simplicity. And our carboxylic acid has only 2. So that kind of tells me we might be splitting this in half. How do we split a triple bond in half, so to speak? Ozone or ozonolysis. All right, and then our last reaction, how would we turn that cyanide group, or that cyano group, into a carboxylic acid? Well, we can just use an acid and heat. Pretty easy. Okay, so that last reaction would actually be a hydrolysis reaction. And then the other 3 reactions, we have oxidation and ozonolysis. All right. Now, there is one other way that we can prepare a carboxylic acid. So we could start with an aldehyde, and this could really be any aldehyde. It doesn't have to be benzaldehyde, which I drew here. And if we want to turn that aldehyde into a carboxylic acid, what could we use? Any thoughts? A peroxy acid. Okay. Now, there is a new method that we haven't really seen before. And this one, well, it's a new method, but it's using materials that we've seen before. So this method uses a Grignard reagent. So the R group is any alkyl group. The X is a halogen, so most likely bromine. And then we've got magnesium squeezed in between those two. So we can actually turn this Grignard reagent into a carboxylic acid. And what we're going to use is carbon dioxide. And that will be a solid, so that's dry ice. So if you've ever seen the ice that immediately turns into smoke, that's dry ice, and that's just made of solid carbon dioxide. And you can just pick that up at the store. And then we'll follow that up with an acid. So that's pretty cool. Just some Grignard reagent and dry ice, and you get a carboxylic acid. So let's look at the method for, the mechanism for this new method. All right, so we've got our Grignard reagent and carbon dioxide. I was trying to say carbon dioxide and kept thinking carboxylic acid. I'm getting tongue-tied with all these carboxy things. All right, so we know on our Grignard reagent that the alkyl group is negatively charged and the magnesium is positively charged. So that negatively charged carbon group is going to attack the carbon in between those two electronegative oxygens, and one of our pi bonds will move over. So if we highlight our oxygens, our blue oxygen stays as a double bond to carbon, and then our other oxygen, we'll highlight purple, is now negatively charged. So in the last step, we just add some acid, probably dilute acid, and that will protonate the negatively charged oxygen. So pretty easy, not too bad to remember. All right, now let's also look at some reactions with carboxylic acids that we've seen before. So let's review some of these reactions. Let's see. So if we want to convert a carboxylic acid into a primary alcohol, so this would be the reverse of that reaction we saw previously, what reagents would we use? Do you remember? You can pause the video if you want to think about it for a little bit. So remember, we would use a reducing agent, and it has to be a strong reducing agent. So we would use lithium aluminum hydride followed by acid. Now, you couldn't use sodium borohydride for a carboxylic acid. Remember, sodium borohydride doesn't work very well for carboxylic acids or esters. We need a really strong reducing agent. So we would have to use lithium aluminum hydride here. And let's just refresh our memory on the mechanism. So in the first step, the hydrogen, or one of the hydrides, grabs the hydrogen from our carboxylic acid. That will move electrons over to oxygen. So now we have our conjugate base. And the aluminum atom with its 3 hydrogens now that are bonded to it So we lost one of the hydrogens in the first step. Now the oxygen in the carbonyl group is going to donate its electrons to aluminum's empty p orbital. At the same time, one of the hydrides is going to kind of move over. So we end up with that top oxygen bonded to our aluminum, which now just has two hydrogens bonded to it. And we've added a hydrogen to our carbonyl carbon, or what was previously our carbonyl carbon. So we've actually created a good leaving group when we did this. So now electrons from our negatively charged oxygen will come down to form a double bond, and our leaving group will leave. All right, so now we have an aldehyde, and we're just going to do all of that again. So a hydride from our aluminum hydride molecule will come in, attack, let's see, we end up forming a negatively charged oxygen. Now we have two hydrogens bonded to that previously carbonyl carbon. And in our last step, we're just going to add a hydrogen to that oxygen through protonation with an acid. So again, this is something we have seen before. It was a long time ago, but it's always good to review. Now, there is an alternate method that we can use to turn a carboxylic acid into an alcohol. So this method involves using borane. So remember, this is borane tetrahydrofuran. And just a quick note that this really only works with carboxylic acids. But you do end up forming that primary alcohol at the end. Now, what's really great about this method is, let's say that you have something with two carbonyl groups. So we have a carboxylic acid on one side, and then let's say we have a ketone on the other side of this benzene ring. The borane tetrahydrofuran will only react with the carboxylic acid. So in our product, our ketone remains intact, and our carboxylic acid is converted to an alcohol. My highlighting is a little messy there. Okay. And then our last reaction that we're going to talk about is nucleophiles. So let's say you have your carboxylic acid, and you react it with sodium hydroxide. So that hydroxide is going to grab the hydrogen on our carboxylic acid, which will leave electrons behind on oxygen, so we get our conjugate base. And now we have a weak nucleophile. So the conjugate base of our carboxylic acid can attack something. Now this is a weak nucleophile because remember it's resonance stabilized. So that negative charge is actually shared between the two oxygens. But we could use something like an alkyl group bonded to a halogen, so an alkyl halide, and the oxygen that is negatively charged will attack the alkyl group. Our halogen will leave, and now we have an ester. Okay, so in this case, you do need a very good electrophile with a good leaving group. In order to perform this reaction. I'm going to add very good electrophile with good leaving group. All right, so next time we're going to start diving into those carboxylic acid derivatives. Here you can already see how we could easily turn a carboxylic acid into an ester. So an ester is a derivative of our carboxylic acid. But we'll talk about other derivatives next time. So I will see you then.